So, like I told you in, I think, day one, most everything is a compound. There's 92 naturally occurring elements, and there's trillions and trillions of compounds in the world. So most everything is a compound. Do you remember how we define a compound? What is a compound? Or if you don't know how we define it, can you give me an example of some compounds outside of the two that are on the board right now, or on the screen right now? Water is a compound. And what's the formula for water? Do you know? Can anybody think of another one? Baking soda, do you know the formula? It's NaHCO3. Can anybody think of another one? Carbon dioxide, CO2. So we can tell by looking at these things that compounds are combinations of different atoms. They're always the same combination of different atoms. Carbon dioxide is always that combination, always CO2. Water is always H2O, right? So they're in that, we've said this before, but they're in those fixed, definite proportions. It's what we call that, all right? They're always in that ratio. The interesting thing about compounds is that they don't have to have any of the properties of the atoms that make them up. Table sugar is, we call it sucrose. Sucrose is a combination of carbons, hydrogens, and oxygen. So carbon is, well, we know two forms of carbon. Carbon is charcoal, right? And the other form of carbon that we know is diamond. Hydrogen is a flammable explosive gas, most abundant thing in the universe. And oxygen is the air that we breathe. That's what makes life possible for humans. We put those things together and we get little white granules of sugar. Salt is made out of sodium and chlorine. Sodium is a soft metal that you can cut with a butter knife. And chlorine is a yellow poisonous gas that's used as chemical weapons. If we mix those two things together and shake it up, boom, we get table salt. Okay? So the properties of a compound don't have to bear any resemblance to the properties of the things they're made out of. So that's an important thing, right? Properties of a compound different from the elements that make it. So like we've said before, some of the things we deal with in everyday life are elements. Most things are not. Most of them are going to be compounds. Free atoms are really, really rare in nature. Things like helium, neon, argon, those things on the far right of the periodic table, those things don't like to react for reasons that we haven't discussed yet, but they're roughly inert. But most everything else likes to react. They like to give away electrons or take electrons or share electrons, and we'll talk about why all that is later. But as a result, you don't really see just iron hanging out in the earth or aluminum just hanging out in the earth, right? It's usually iron mixed with oxygen or carbonate or something like that. And so we get these, most everything is made of compounds. And it's different from a mixture in the fact that it displays this constant composition, right? And that we keep coming back to this fixed, definite proportions. And all that means is that if you have a compound, it's always an atom ratio, and it's always that same atom ratio. Remember, mixtures, we can willy-nilly make whatever we want, right? We just add a little more of this, add a little more of that, and we can change the composition however we want. Compounds, we can't. They're stuck. So we could make a balloon here that was a mixture of hydrogen and oxygen, and we could vary how much hydrogen, how much oxygen was in that balloon just by pumping it in there. And I can change that composition however I want. But if I fill a balloon with water, that ratio of hydrogen to oxygen is fixed. There's 2 hydrogens for every 1 oxygen that's there, and I cannot change that because that's how water works. It's always that way. Doesn't matter if I get it out of the sink, if I get it from Antarctica, if I get it from the polar caps in Mars, it's always H2O. This idea was kind of formalized by this guy, and I don't care if you know his name or not, but he stated the law of constant composition. All samples of a given compound have the same proportions of their constituent elements. That makes sense if we're looking at the symbols for compounds, okay? Remember that this stuff was done in the 1700s, early 1800s. They didn't have fancy technology like we have now. So everything that they did had to be done on the big scale, right? So basically the way that they dealt with everything is they weighed it. And so they calculated ratios of compounds by looking at the masses of the atoms that were present. If we were to take, say, 18 grams of water and we were to decompose that which we can do pretty easily. You can take a 9-volt battery and you can stick a wire on each lead of that 9-volt battery and stick it down in water, and you can get little bubbles, and you're decomposing the water into hydrogen and oxygen, right? So if we were to do that, we get 16 grams of oxygen, 2 grams of hydrogen. And so there's a ratio there, a mass ratio of 16 grams of oxygen to 2 grams of hydrogen, or 16 to 2, or 8, or 8 to 1. And so we're gonna take you back to math for just a minute. If we're writing a ratio, we can write a ratio as a fraction. This is the result of that fraction. Or you can write a ratio with a colon, like this right here, 8.0 to 1, or 16 to 2. If we're translating a ratio into a fraction, the thing that's on the left becomes the numerator, the thing that's on the right becomes the denominator. But what we care about is the fact that water always has this ratio. We said the other day that we could count atoms by weighing them, right? So what was the first step in that? If we wanted to count an atom by weighing it, what do we do? Moles. We need to go to moles, right? So how do we go to moles? Periodic table. We find the atom on the periodic table. What do we do with it? This is the most common calculation you'll make in all chemistry, and this is something you got to be able to do half asleep, okay? So how do we convert from grams to moles? So we at that point call it the molar mass, but absolutely, yeah. Right, so we go to the periodic table, we look up oxygen, we see the number 16.0, or maybe 15.99, okay? What that means is that that's 16 grams of oxygen for every 1 mole of oxygen, right? That's the conversion factor that we get. So you tell me, looking at this sample that we've got right here, how many moles of oxygen are there? All right, so now go to the periodic table and find hydrogen. And what is the molar mass of hydrogen? Pretty much 1. 1.01 or something like that, right? Tell me how many moles of hydrogen are there? 2. So we got 2 hydrogens and an oxygen, water, right? So that mass ratio that's always the same is always the same because the atom ratio is always the same. By writing these formulas for compounds over here, we can see how many atoms are there. Those atoms then give us a mass ratio that's always the same. They, in the 1800s, did it the other way around, right? They had to do it on the basis of mass because that's what they could observe was mass, right? So that's why you see all these things formulated from that point of view. We know now that it's that mass proportion because the atom proportion is that, right? So every compound is unique in whatever it is, and so when it has that atom composition, it will have a particular mass ratio that is unique. So if we looked at ammonia, ammonia would be the same kind of thing, right? If we took 17 grams of ammonia, it would break down into 14 grams of nitrogen, 3 grams of hydrogen. If we did the same calculation that we just talked about for water, and we went to the periodic table and we looked up nitrogen, we looked up hydrogen, we would see that this is NH3. So this particular mass ratio of nitrogen to hydrogen comes about because of the atom ratio. So atoms combine in whole number ratios, right? This is 1 to 3, atom ratio. But the mass ratios don't have to be whole numbers. They can be fractions or decimals or whatever. But the atoms always combine in whole number ratios to form a compound. 1 of this, 1 of those, 1 of this, 2 of those, 3 of these, 5 of those, whatever it happens to be, okay? But it's always whole numbers. So again, we use chemical formulas to represent these things because nobody wants to write out the names of all the things. Again, that mass composition comes about because of the atom ratio, and that's what we write down. If we write a compound down, we write the symbol for the atoms that make it, with a little subscript to tell us how many of that atom type are there. So when you see that H2O, it means that we have 2 atoms of hydrogen to every 1 atom of oxygen. That also works on the basis of moles. So if we had a mole of water, which is how many atoms again? That's the number you guys need to know. 6.022 times 10 to the 23. So 1 mole of stuff is that many things, right? So 1 mole of H2Os would have how many oxygens? So if I got 1 mole of H2O, how many oxygens is there? 1 mole of oxygen, right? For every 1 mole of water, there's 1 mole of oxygen, right? If I got 1 mole of H2O, then I got 1 mole of oxygen. Do you agree with that? How much hydrogen would I have? I'd have 2 moles of hydrogen.